So in this topic, we're going to talk all about electrostatics, static electricity, like what happens, what is it, how's it, what comes about, how charge is created, all that fun stuff. So, so here's some pictures of some static electricity going on. So you have the nebula balls that you guys might have played with. See a person back that's got a Van de Graaff generator we're going to play with. Mine's not quite that good where it's going to get people's hair to do that, but we'll do our best. There's a cat that's rolled around in some styrofoam peanuts, and all those styrofoam peanuts are stuck to it. So how does that actually happen? So the first step, well, what makes up everything? Well, it's atoms, and there's our key. So we have charged subatomic particles are the key for atoms. So we have our electrons, which are there on the outside. Those are negatively charged, nearly massless particles that are moving around on the outside of every single atom. There are some that are more loosely attached, which are called valence electrons. Those are the ones furthest away from that center thing called the nucleus. That nucleus is where you have your subatomic particles tightly held together, and those have both positive and neutral charges. So those two particles are going to be your protons and your neutrons. The protons are the ones that we're going to really care about for electrostatics because they have that positive charge. And neutrons are the non-charged particles in the nucleus that help provide mass. The big thing is that nucleus is stuck. It's not going to move around. But those electrons are free moving around the outside, being held in by that positive charge, but we can actually manipulate that. But first off, a little quick thing, reminder about what do charges do to each other. Well, like charges are going to repel, so there's got to be a lot of attractive forces going on in the nucleus holding those positive charges close to each other, and there are. But that's not going to be part of what we're dealing with here. But the electrons are going to repel away from each other, so they're not really going to want to be super close to each other. They will move around a little bit since they're free to roam around in the space around the nucleus. And then opposite charge is going to attract. So that nucleus is holding on to the electrons from the outside. So the nucleus with that strong positive charge, those electrons out here, they're being held onto it, right? And you'll learn this more in chemistry next year, but those ones that are furthest away, they're going to be pretty easy to take off, depending on what the material is, depending on the structure of it. So you'll learn more about that in chemistry next year, but understand that those electrons can be stripped away. So, what determines how much force there is? Well, that's a thing called Coulombs Law. Don't really worry about the math too much. You're going to do a little activity with this just to explore the relationships between charges and distance. But you can see here, K is just some constant electrostatic constant, not a big worry. Q1 and Q2 are just the amount of charge. So you might have a charge here that might be like 100 electrons, and over here you might have another charge which is like 500 electrons. These are just numbers and examples, okay? So just talking about how much charge there is in the two objects that have a charge. R is just the distance between the two of them, okay? So if you have 100 electrons over here and 500 electrons over here, okay, the further away they are from each other, the less charge there's going to be, since R is in the denominator. And you'll play around with this in the Coulombs Law activity that I sent you guys. It's pretty quick, but it's pretty good in terms of informing the differences between those two. Again, we're not going to worry about actually calculating what this F is. If you want to get, when you get into AP Physics, you'll need to do that. But for now, you should be fine with just understanding that as the amount of charge increases, the force is going to increase. As the distance increases, the force is going to drop, but not just linear. Again, we see that square term is going to be the key there. Kind of going here. So one thing to note too, a positive force is repulsive and a negative force is attractive. So if Q's are both negative, negative times a negative means it's going to be a positive, F will be positive, and two negative charges, those forces will push away from each other. If Q is positive, Q1's positive, Q2 is negative, well, F is now going to be negative, and those forces will attract each other, so that negative force is one that's going to draw things in. So just a couple of quick notes about Coulombs Law. Again, don't worry about understanding the math behind it, getting numbers. We're not going to do that. So how are those charge differences actually established though? That's the key, right? You don't have a difference in charge, you can't have it. Most atoms are neutral, meaning that they have the same number of protons and electrons. So there's no difference in charge numbers. Okay? The plus and minuses perfectly balance each other. A positives and negatives perfectly balance each other out. Well, we can deal with that in a couple different ways. One, we can have conductors. We have two different types of materials we're going to deal with. So conductors, they are metals that are going to allow for electrons to move freely about. They have what's called a sea of valence electrons, and I'll show that in a second. Um, but things like copper, silver, gold, aluminum, those things, they're good conductors because electrons can move freely within them. We have other things which are insulators. So in this case, the insulators are all the coatings on these wires. They don't allow for easy electron mobility. The electrons are kind of trapped there. You can rip them off, but they can't freely move about because of the properties of the material. So in a metal, all we have to do to get a charge difference is kind of push the electrons one way or the other. So this might be like applying a battery to a wire, or plugging a wire in, right? So if we plug a wire in or apply a wire to a battery, or apply a battery to a wire, we can use the fact that batteries have a negative end and a positive end. We attach that to some wire here, and this negative end is going to cause electrons to start moving through. And this is more current electricity. Um, but it's important to understand that in metal, it's pretty easy if we have something with a charge to induce a charge in that other object because we can easily get electrons to move across. But one thing you'll notice is that even though the electrons move around all over the place, the protons are stuck. So when we bring charges close, we're only going to influence the direction of electron movement, not protons moving around. Protons are going to be stuck in one location. Okay, it's great. Metal things are easy to move around, but insulators. These packing peanuts are obviously not metallic, but yet they're sticking to this thing. And they're sticking to it by static electricity. They're sticking to it by charge differences. So what happens? Well, that's where friction comes in. So here, you all have done this probably before when you were a kid. You rub the balloon on your head, and all of a sudden your hair sticks to it, or it sticks to a shirt, or it sticks to a wall. Well, what it's doing when you generate that friction, you see over here on the right, is the object is actually going to start stripping electrons away. Now, I know in this picture it looks like all the electrons go. Not true, but some of them go. All you really need is the fact that maybe this balloon would be negatively charged and the person's hair is now positively charged because that friction has stripped some of those electrons away and now they're on the balloon. So here's another example, kind of that example of a balloon on a wall. You see the balloon has excess negative charge on it here, and that's going to cause these electrons to start moving away in the wall. Now, it's not a metal, so they're not going to like flow out and away, but they just shift away, which means the side of the wall closest to the balloon is positive, while the balloon is negative. And if that's the case, those two things are going to attract. So that's why the balloon, when you rub it on your head, actually gets stuck to the wall. Assuming the weather is good. Sometimes if it's too humid, it won't work. But so that negative and positive interaction here at the wall will hold that balloon there due to those electrostatic forces. You also see it up in clouds and getting lightning. Okay, it's all about static electricity. So you have excess electrons building up in the cloud, and that's going to cause the tree closest to it, okay, to actually lose its electrons. Those electrons aren't going to go to the cloud. They're actually going to go into the ground because they're going to be repelled by that strong negative charge in the cloud. So as these electrons start to move away from the cloud, the top of the tree becomes positively charged. Eventually there's enough difference of negative and positive charge for electrons to jump, and they'll jump through the air, kind of jumping from particle to particle in the air and making their way down to the ground, making their way to that positive point. Okay? Lightning can also jump from cloud to cloud. You have a negatively charged cloud, you might have a positively charged cloud. All the friction has caused it to lose its electrons. They've gone to some other source. Well, then that lightning could actually jump across from the excess negatively charged cloud to the positively charged cloud. Okay? Or this positively charged cloud could draw electrons up towards it from the ground, and they'll make their way up to the top of this house. And now, it seems kind of weird, but the lightning actually travels from the ground up. Okay, and that's totally plausible. It happens all the time. Okay, it all depends upon the charge of the cloud as to which way the electron movement is happening. And it all depends on like what's happening in different conditions in the clouds, which cloud's getting what. You could also have a cloud that has a negative end and a positive end, right? And that would have a lightning strike within the cloud itself if the differences get too big between the top and the bottom. So there's lots of different ways you can have lightning happening, but it's all about charge difference and electrons repelling or electrons being repelled or attracted based upon wherever they have traveled to. So what happens in this is you have a thing called polarization. So polarization is when a charged object moves towards another object. Then that object becomes polarized. So here we have a positively charged glass rod. Well, you have a neutral sphere. Okay, there's no extra electrons, there's no extra neutrons. The charge here, so it might have, so just as numbers wise, it might have 60 electrons and 60 protons. Totally not true. It has way more than that, but that's okay. But some of those electrons have been attracted over to the positively charged rod. The positive charges have not been repelled to the other side. Remember, the positive charges haven't moved anywhere. So when I think about this initially, this ball here would have looked something like this, where both sides were perfectly balanced. Okay, but as you brought that positive charge close, electrons from this side started to make their way over. That is left the left side with more electrons than protons, so it is slightly more negative. The other side is more positive. This is the process of polarization. Polarization is when the object is still neutral, but it has a negative pole and a positive pole. So think about in the lightning example, the house has become polarized, okay, because the electrons are being drawn towards the top of it, and it has protons at the bottom. Now it might have excess electrons, so it might not be neutral anymore, but it does have a negative side and a positive side. I've done this without even touching it. That's kind of the key. This positive charge rod did not touch that thing at all. But we can induce charges in objects. We can get real objects that actually get those charges in the objects. So if we bring this negatively charged rod close to this metal ball and we touch it, well, some of those electrons are actually going to jump off. I'm going to diagram this out a little bit better. So if we have our negatively charged rod here, we have our ball. As we bring it close, where are electrons going to go? Well, electrons are going to shift away, which means this side will be more negative because they're being repelled, and this side will be more positive, okay, because electrons have left. If this side is more positive and we touch it with something that is negatively charged like we did here, so this side would be more positive, well, those electrons are going to be attracted to those excess positive charges and actually leave our object and jump onto the metal sphere. Now, once those objects have jumped on the metal sphere, we take the rod away. That sphere will now have excess electrons on the left, and it would still have electrons on the right. So overall now, because we added electrons to it, we have a net negative charge on the sphere. Okay? So that's charging by conduction. You're directly touching the object, you're conducting a charge onto it. Okay? We can also charge objects by induction. So in this case, we have two metal spheres. We bring a negatively charged object close to it, causes electrons to shift away. So we have a positive charge here on the left and a negative charge here on the far right. But electrons have actually moved from A to B because they are touching and because they're both conductors. Now we pull sphere B away, and because sphere B has extra electrons compared to from the initial point, because it got electrons from A, sphere B now has a negative charge. Okay, A is still polarized with positives here and with positive and negative charges, but some of its electrons have gone to B. So now A has lost electrons and has a positive charge, and B adds electrons and has a negative charge. So really we're inducing charge here because we never actually touched an object. We just forced electrons away to another point without actually touching it or adding electrons or taking them directly away from it. Okay, we just induce them over from A into B. Hopefully that makes sense. We can do another way of, we also can do induction with grounding. So grounding is when you touch an object and you neutralize it. Okay, so by touching it, you can either add or take electrons away, and that will cause the object to be neutral. Because things don't really want to have a charge; they'd rather be neutral. Okay, but here's induction by grounding. Positively charged object comes close to a neutral sphere. Electrons move towards it to the left. So now my ball is polarized. I had a positive charge over here, but now I'm going to touch it. Well, that positive charge doesn't want to stay positive. It wants to be neutral. And my hand is a great source of some extra electrons. So extra electrons are actually going to go into the ball when I touch it there. Okay. And by doing that, now I've neutralized that left-hand side. By putting electrons in, this left-hand side is now neutral. So this would be plus, minus, perfectly balanced out. The left-hand side is still negative because, well, electrons are still being pulled in this direction towards that positively charged object. So by adding extra electrons, when I take that object away, to my entire sphere, I now have more electrons because of when I touched it. So now I have a negatively charged sphere. So all of these three ways working together, inducing charges and objects, are different ways to pass charges on from one thing to another and show the interaction between protons and electrons, how they attract, how they repel each other, and what that relationship is. The key takeaways for this whole thing are major things. Electrons move, protons don't. Okay? Okay? Positive charges, they may be attracted to a positive charge, but they'll never move within a conductor. They'll never move within another object. The electrons are the thing that's going to shift. So the electrons will shift either towards a positive charge or away from a negative charge. Protons do not move. To repeat, protons do not move. Okay? Just to make sure you're clear on that. Those protons are stuck in that nucleus. They're stuck in that atomic structure. They are not going to start shifting around all over the place. Okay? Your electrons will move. They can transfer from one side to another or shift within an atom. Totally fine. Protons are stuck where they're at. Okay. So hopefully that makes sense. Okay. Hopefully answer the question with the play pause and they helped. And we'll go through a bunch of demonstrations on Thursday and Friday.